radioactive elements. We discuss about the radioactive elements and how do they work, and we discuss about the unstable nuclei in this chapter. Okay, and there is half-life period, undecayed atoms, and all that we will discuss in this lesson. Now atom mass and composition of nucleus. So we start with AMU. Okay, 1U or 1 AMU. What is 1 AMU? This is atomic mass unit. Okay, atomic mass unit. What is the definition of this? Suppose if you break C612 is the isotope. Again, what is the isotope? Isotope means elements, same atomic number but different atomic mass. Same atomic number but different atomic mass. They are said to be isotopes. Okay, we are taking C612 isotope and we are breaking that into 12 parts. Then that one part will become 1 AMU. That one part will become AMU. See, that means what? You are taking the isotope. Okay, you are taking this isotope. So 1 AMU is equal to what? 1 by 12 of C612. 1 by 12 of C612. Okay, C612 atom. That is said to be 1 atomic mass unit. Now, what is the definition of isotope? Isotopes means? Yeah, nuclei we can say, or atoms with same atomic number. Yeah, same atomic number. But different atomic mass. Okay, different atomic mass. Okay, different atomic mass, same atomic number but different atomic mass. So that is said to be isotopes. So example for isotopes is what? Example is C612, C613 and C614. Next is isobars. What is isobars? Isobars means atoms with same mass number. Same mass number is said to be same mass number of different elements. Okay, so example for this is what? We have C614 and 714. Okay, C614 and 714, these are the examples. Next is we have isotones. What are isotones? Atoms with same number of neutrons. Atoms with same number of neutrons. Atoms with same number of neutrons is said to be isotones. What is the example? Example for isotone is same number of neutrons, right? C613 and 714, 0815. Okay, so this is the difference. The difference between 13 and 6 is, so what is atomic number? How do we define atomic number? Did we complete the atoms part? I didn't do that, no? No, you didn't tell me that. I'm thinking I'm done with the. I'm done with this. I was thinking about that. Okay, let me just finish off this atomic number. Both are independent, no need to worry. Okay, atomic number means number of protons. Number of protons in an atom. Number of protons in an atom is said to be atomic number. Number of protons in an atom is said to be atomic number. So, atomic mass means atomic number is represented by Z. Atomic mass is represented by A. Okay. Atomic mass is represented by A. Number of protons and neutrons. Number of protons and neutrons present in the nucleus. Present in the nucleus is said to be atomic mass. Okay, atomic number of protons in an atom, number of protons and neutrons present in the nucleus. So A equal to what? A equal to Z plus M. Okay, what is capital N? Capital N is number of neutrons. Okay, number of neutrons. If you want to calculate the number of neutrons, where N is equal to what? A minus Z. Okay, you want to find out the number of neutrons, just take N equal to A minus Z. Okay. Okay, so this is how, see once again, when atomic mass unit is equal to 1 by 12 the atomic, that is isotope of C612. If we break that C612 into 12 parts, that one part will become 1 AMU. And isotopes means what? Number of atoms is same number of same atomic number but different atomic mass. That is isotope. Isoparts means same mass number, and isotons means same number of neutrons. Now atomic number. What is atomic number? Number of. So atomic number means number of protons present in the nucleus, present in an atom. Okay, number of protons present in the nucleus. Okay, we cannot in an atom or in a nucleus. Okay, so present in a nucleus. So we can also say electrons, but electrons differ. That's the thing. Because once they involve in ionization process, the number of electrons will not be stable. It will change. Next is atomic mass. Number of protons and neutrons present in the nucleus is atomic mass. A equal to Z plus N, and number of neutrons is calculated N equal to A minus Z. Okay. Now, so again about electron, proton, and neutron, that I have to discuss now. Okay, electron, proton, and neutron. We'll discuss them. Then we will go ahead with the okay. So also, if you want to write in terms of kg, one atomic mass can be written as 1 U is equal to what? 1 U is equal to 1.66 into 10 to the power of minus 27 kg, which is equal to mass of proton, which is again equal to the mass of proton. So now I'll continue this nucleus. Okay, let me finish off nucleus. What I have done with the, I'm done with the atoms. So tomorrow I will teach you atoms. Okay. Just 2 minutes. It also important class.
But my handwriting was bad again.
I'll erase this now, this side. Okay. Now, here we have mass of proton. So, in terms of atomic mass unit, mass of proton is written as MP 1.00 1.00727 U. Mass of proton is 1.700727 U. Similarly, mass of neutron is 1.00866 U. You already know that mass of neutron is greater than mass of proton. Okay. Mass of neutron is greater than mass of neutron. That already we know. Now, so size of the nuclei. How to find out the size? See, the nucleus is in nucleus is in spherical in shape. Nucleus, an atom is spherical in shape. So he has found out the size of the nuclei. So before going to this, I would like to discuss about electron, proton, and neutron also. So electron was discovered by J.J. Thomson. J.J. Thomson has discovered electron, and charge of electron was discovered by R.A. Millikan. Okay, R.A. Millikan. And charge of electron is how much? Negative. Charge is negative. It is negative, and the charge of each electron is minus 1.602 into 10 to the power of minus 19 coulombs. Mass of electron is 9.11 into 10 to the power of minus 31 kg. Okay, the symbol is what? E minus 1, 0. Next is what? Proton. Proton was discovered by Rutherford. Okay, the charge of proton was discovered by Goldstein, and it is positive in charge. And charge of proton is plus 1.602 into 10 to the power of minus 19 coulombs. Mass is 1.66 into 10 to the power of minus 27 kg, and symbol is P1 and 1. Now, now we'll go with neutrons. Here, neutron was discovered by Chadwick. Charge of neutron is how much? Charge of neutron is 0. And mass is how much? Mass is 1.67 into 10 to the power of minus 27 kg, and that's it. The symbol is N01. This is about electron, proton, and neutron. And size of the nuclei. Nucleus. How much is the size of the nucleus? It is given by R is equal to R naught. Okay. Size of the nuclei is found, that is, it was found in the Rutherford alpha static model. R is equal to R naught a to the power of 1 by 2. Okay. R is equal to R naught a to the power of 1 by 3. R naught value is equal to how much? 1.2 into 10 to the power of minus 15 meters. So,
R is the radius.
Radius, yeah. R naught is said to be unit radius, okay? Now, next comes mass energy and nuclear binding energy. Mass energy, and this is said to be unit radius, okay? That in that atom structure is A0. A0. Now next one, mass energy and nuclear binding energy. Mass energy and nuclear binding energy. Mass energy and nuclear binding energy. So we'll start with mass energy. So Einstein, in his, I told no, in 1905 he published some few papers. In one of them is mass energy equivalence relation. Mass energy equivalence relation. So we have the equation. What is that? E is equal to mc square. Okay. E equal to mc square. Where c is the speed of light. 3 into 10 to the power of 8 meter per second. What exactly it is? See here. If you burn 1 kg of coal, you get a lot of energy, right? So his concept was, can we convert energy into mass? You understood? See, when we burn something, we get energy. Whether it is any fuel or anything, if you burn, we get energy. But can we convert that energy into mass? That was his concept. Yeah, we can do it. But it is only applicable for the micro and nanoparticles, very, very small particles. So what is that? He tried with electron pair production and annihilation. Annihilation and production. Okay, he went with that concept. So annihilation, pair production and annihilation. Okay, so annihilation. In annihilation, what he will do is, like a electron and a proton, positron, and for every particle there is an antiparticle. So electron and positron come together and we get a wave. This is our h nu. Okay, that means the particle mass is converted to energy. This is particles, right?
Yeah.
This is mass that is converted to energy. When a electron and positron come together, they release energy. Okay. So next is what? A pair production. In pair production, if they scatter, this what is happening? You know, when this is a h nu, it scatters into two. What is that? Electron and positron. It's only under certain conditions. It's not everywhere. It happens only at certain conditions. So pair production. So that is how he want to convert that energy into mass and mass into energy. It was only possible at but annihilation or conversion of mass to energy is possible at any level. That's not a problem. But conversion of energy into mass is only limited to certain conditions. Okay. That was his concept. Okay. Next is binding energy. Clear, Joshua? Now we'll go ahead. What is deleted from this lesson? I'll tell you, don't worry about that. Only I'm teaching the thing which is there in the syllabus. Now, binding energy, nuclear binding energy. Nuclear binding energy. So before teaching, so before going ahead with the binding energy, first I would like to discuss about the mass defect. Okay. So mass defect is what? Delta M. Mass defect is delta M. Means what? The difference between actual mass, and calculated mass. The difference between actual mass and calculated mass is said to be what? Mass defect. Difference between actual mass and calculated mass is said to be mass defect. Now see here, how do we calculate the calculated mass? First I will discuss about the calculated mass, then I will tell about the actual mass. Calculated mass is very simple. How do we calculate? That is equal to Z into MP. Means number of protons into mass of proton. Number of neutrons is what? A minus Z, right? A minus Z into Mn. This is calculated mass. Okay. So next is what is that? Actual mass. How do we get actual mass? Actual mass we get from the periodic classification table. That is M. Okay. This we attain from periodic classification table. And from where do we get that also again? Periodic table or periodic classification table. That also again from where? This is using mass spectrometer. Mass spectrometer. Again, there is an experiment. What do we do in mass spectrometer experiment? In chemistry it is there. Mass spectrometer, first we'll take one, suppose I have 1 kg of carbon. I'll take it as it is, which is from the earth crust or somewhere. And what happens, first I will convert it into gaseous form. Then I will pass it through the magnetic and electric and magnetic passage. Then what will happen? They get separated. And from that I came to know that 99.8% is C612. Understood? That is mass spectrometer. Suppose if I take like C612, maybe 89% is C612, and around very small percent, 0.01% is maybe C613, and C614 still more less than that, 0.001% is C614. So we came to a conclusion that then in the periodic classification table they have given C612. They did not give 3. Otherwise our periodic classification would not be of 114 elements. It would be around to 500 elements. Understood now?
Yeah.
So we have taken only because it depends upon the isotopes. So this they calculated using mass spectrometer. From there we got that atomic mass in the periodic classification table. Understood now? Got it? So this is the the story behind writing that particular number in the periodic classification table. Now, so what is the difference now? The difference between here. So here we have delta m equal to what? Calculated mass minus actual mass. Okay, Z into MP minus A minus Z into Mn, A minus Z into Mn minus capital M. That is delta M. That is said to be mass defect. Okay. Now we want to find out the binding energy. What is binding energy? Binding energy means, okay, before going to binding energy, I'll just tell what is nucleons. What are nucleons? Nucleons means protons and neutrons together are known as nucleons. Protons and neutrons neutrons are known as together nucleons. Okay, protons and neutrons together are known as nucleons. Okay, you are known as nucleons. So what is binding energy now? Binding energy is EB. Okay, binding energy means amount of energy required to separate a nucleon. How much energy, amount of energy required to break and separate them, required to separate a nucleon. That is said to be binding energy. Or to separate or to bring both the nucleons together. Either to separate or to bring the two nucleons together is said to be binding energy. You can say in both the words. So EB is equal to what? EB is equal to delta MC square. Just calculate in this way, we will get the answer. So you can write here delta capital M. Instead of writing small m, you can write delta capital M. That is mass defect. Mass defect into speed of light. Okay, square of the speed of light. The next is the graph is very important. That I'll explain now. Then comes nuclear process. A small chapter. Okay. The atoms is also small. Done. So I'll go ahead now. So Next is binding energy per nucleon. Binding energy per nucleon. It is written as EBN is equal to EB by E. Okay, binding energy per nucleon. So the ratio the binding energy EB, the ratio of the binding energy EB of a nucleus to the number of nucleons. Of a nucleus to the number of nucleons, capital A. This is to what? Binding energy per nucleon. So we write EBN. Binding energy per nucleon is written as EB by capital A. Okay, this is the formula of it. Now there is a graph here. I'll just plot the graph here. This graph is important. They have asked this graph many times. Zero, 2, 4, 6. Just increase the size better. Two, 4, 6, 8. Then comes this is 50. 100. So this is mass number or capital atomic mass is in this way, and binding energy per nucleon, EBN. Okay, EBN in million electron volts. It is on y-axis. Now, now this graph is important. Why? Because from this graph we were able to find out for which element how much energy can be released. Okay, like we are applying this formula, right? How much energy is released for one nucleon for that particular atom. We are able to find out that we can use that for particular constructive purpose. But nowadays people are using for destructive purpose. That is a different thing. Okay. Huh? So mass now the investigation is going on. So is it to separate the protons and neutrons? Yeah, that is correct. That is. Yeah. So now when they are really living that one, in so many cities they are finding so many hundreds of dead bodies. So again, this is a what international media is doing and what other countries are doing. Just you are passing a resolution, but it's of no use. Okay. Now here it is like this is 1H2. This is 1H3. Okay, 1H2 and 1H3. This one is hydrogen 1H2 and this is 1H3. Okay, and then comes helium, which is somewhere here. He, that is helium is He24. Helium is He24. Then comes lithium. Okay. Okay, lithium. So lithium. Then we go to the carbon. Carbon C612 and nitrogen. Carbon C612. Then comes nitrogen. N714. There is nitrogen. And then comes oxygen. Okay. Like here it is oxygen. O860. Then comes O818 like this. It comes in this way. Okay. Somewhere about O818. Make it little bigger so that it will be easy for you. Now then comes sulfur. Sulfur is somewhere here. Sulfur 32. Then iron. Then Fe. Then MO. What is the name of that element MO? MO means yes, any idea? What is MO? Go to the Google, okay, and search what is MO. Going to write now grade 12 exams, board exams. No? ANNU. No? This science?
So it's from this one is a DNF block.
Yeah, then what is that? S means sulfur, okay, accepted. Fe means iron. I means iodine, okay. What is M? What is W? What is An? U means uranium. Okay. Molybdenum, yeah, very good. It is a heating element like chromium. Chromium, we have chromium, no? This is used in the bulbs, okay. Molybdenum. So, tungsten, molybdenum, they are having very high melting point. That is the reason they are used in the bulbs. Okay, and also what is W then?
This is
Search, come on. And now we have to discuss about the behavior of this particular graph. Why the graph is like that, and what is the message which we get from this particular graph.
oh, it's tungsten.
Tungsten is different.
Just now I told, no? W is tungsten. What is the tin?
Tin is TN, right?
No, then is
Oh,
PV is lead. Then is SN.
SN.
Very good. What is antimony then?
Oh,
AN.
no.
What was that? SB.
Yes,
That's
yes.
right.
Then what is An here? Come on, go back again. Yeah, that's correct. Tungsten. Correct. You're sure. You're right.
I type an element and Google is showing.
What is that? Is it AU or what? 197. Just type atomic number 197. Is it AU or what? Gold. $197. This 197, yeah. Atomic number 197. Sorry, atomic mass, not atomic mass 197. Gold, very good.
AN.
That is AU actually. There is a mistake in the gold. Yeah. AU is gold. What is atomic number?
197.
197. Yeah, that is a mistake in the book. Okay. That's not AM, that's AU. Okay. Now, see, what did we find? See, from 0 to 25, see, approximately 20, correct?
Yeah.
From 0 to 25, the binding energy per nucleon is increasing. See, for hydrogen, helium, and it kept on increasing up to 10. Okay, from that is up to 10 means up to 5th element. This is up to 25 means up to 10th element. Yeah. After 10th element, after neon, maybe approximately neon, then you can see there is a uniform increase. There is a uniformity. It is constant. It remains binding energy per nucleon remains constant for all the elements. Its maximum, I think, for iron. After that, it keeps on decreasing, but it doesn't decrease steeply. Very small variation is there. Okay, very small variation is there. Now, what are the following features of this graph? We'll discuss the features of this graph. Okay. What are the features of this graph? Number one.
So we have to draw this graph.
Yeah, you have to draw this graph. Okay. The main features of this plot. What are the features? Number one, binding energy per nucleon is practically constant. EBN is constant. EBN is still constant, independent of atomic number and independent of atomic number. Independent of atomic number for nuclei of middle mass number. For nuclei of middle mass number, that is what, A less than between 30 to 170, almost all it remains constant. Okay. And the curve has maximum. The maximum value is what? 8.75 MeV, million electron volt. For A is equal to atomic mass, A is equal to 56, and the value is what? EBN value is the maximum value, that is EBN. Okay, EBN value is 7.6 MeV for what? For A is equal to 238. Okay, so the maximum value from this graph we found that binding energy per nucleon is 8.75 MeV. For A is equal to 56 and EBN is equal to 7.6 MeV. For A is equal to 238. Okay. Now the second one. So the second feature is what? EBN is low for A less than 30 and A greater than 170. EBN is low So there are two features. EBN is constant and independent of atomic number for nuclei of middle mass number between 30 to 170. It is constant and maximum value is 8.75. for atomic number 56 and minimum is for 238. Okay, atomic mass 238. Now, next going to the conclusions. Okay, we'll go. There are 4 conclusions they have given here. We'll do that. So, isn't atomic number of molybdenum 42? So, won't it be before Fe? Yeah. What is that I have given here? MO is C. If you look into the graph, then what is it? 56 is it? No? Atomic mass is what? 56. 56. I think it is for iron. Yes, Mr. Joshua. 56. I think it is for iron. Okay. Sir, 42. 42 is for what? Iron is 42. Atomic mass.
Iron is 20. Atomic number for iron is around 28, 26.
Then what is atomic mass?
Atomic mass will be around 54.
56 it is now. Yeah.
56, yeah.
Yeah, that's what it is giving 56. Got it now? Not the molybdenum. See in the graph it is Fe is max. See? You can think in this way. Fe. Fe is maximum in the graph. Understood now? For molybdenum. For molybdenum, no idea. We need to calculate them. Okay. Now, conclusions. So, what are the conclusions? What are the conclusions? The conclusions are the force of is attractive sufficiently strong to produce a binding energy of few MeV per nucleon. Okay. The force is attractive. The force is attractive and the force is attractive and sufficiently strong to produce a binding energy of a few MeV per nucleon. The second one. So the constancy of the binding energy in the range 30 to 170 is a consequence of the fact that the nuclear force is a short ranged. Okay, the nuclear force is short range. So here, so what is that? The constancy. The constancy of binding energy in the range 30 less than A less than 170 is a consequence of fact is the consequence of the fact that nuclear force is short range. Nuclear force is short ranged. Nuclear force is short range. Okay. Third one. Nuclear force is short range. Understood? So the first one is what the force is attractive and sufficiently strong to produce a binding energy of few MeV per nucleon, million electron volts. Million means 10 to the power of 6. Okay, the constancy of binding energy in the range from 30 to 170 is because of the consequence that nuclear force is a short range. So first one is we came to conclusion that it is attractive. Second one is it is a short range. We came to conclusion that it is a short range.
So only between 30 and 170.
Yeah, they say. From this we came to conclusion it is short range, because you know short range means how much? 10 to the power of minus 15 to minus 16 meters. Very, very small. The attractive force you can feel between the two nucleons is how much? 10 to the power of minus 15. That is the range, minus 15. Very, very, very small. Okay. Very, very small. Next one. Heavy nucleus, that is A equal to 240, has lower binding energy per nucleon. Okay. Alright. Can I erase this? Okay. Now, next point is a very heavy nucleus. Fourth one. Very heavy nucleus. What is that? A is equal to 240. A equal to 240 has lower binding energy per nucleon. Has lower binding energy per nucleon. Lower binding energy per nucleon. Okay. With A is equal to compared to that of A is equal to 120. Compared to A is equal to 120. So this is the value. Now this implies energy would be released. Okay. It implies energy would be released. Okay. Energy would be released. Okay. That is why these radioactive elements are greater than, atomic mass is greater than 240. Okay. So they have like from 120 to 240 we use that for radioactive elements. Okay. So very important implication of energy production through fission. Okay. This can be used for implies energy is released would be released, and gives the concept for fission. Okay. The fourth one. The fourth point, he says that consider two light elements A less than 10 or A less than or equal to 10. So the joining of two form a heavy nucleus. Okay, binding energy per nucleon fused of the fused heavier nucleus is more than the binding energy per nucleon of the lighter nucleus. So this means that the final system is more tightly bound than the initial system. Again, energy would be released in such a process. Okay, it gives the concept of fusion. Okay, it implies energy would be, what he is saying, energy would be released. Okay, it implies energy would be released. And gives the concept of fusion. Okay, I'll tell you what is fission and fusion. So every point is giving some of the other information. The first one gives the information of attractive. It gives the information of attractive. The second point it gives the information of short range. And third one it gives the information of fission. And fourth one gives the information of fusion. When fusion is possible, means fusion is possible for the atomic elements of atomic number less than 10, and fission is possible for the elements whose atomic number is greater than 120. Okay, so that is how it gives the concept. When A is between 30 to 170, it gives the concept of what? Attractiveness, attraction between the nucleons. Okay, and the first one it gives what we call that is the short range. The second one gives the short range, and the first one gives the concept of attraction. Okay, now we'll discuss about the nuclear force. Clear, Joshua? Now, yeah. Okay. So this graph is very, very important. Please do learn this graph. Okay. So they will be asking. Sometimes they can also frame a numerical on this graph. They can also frame a numerical on this graph. That also there is a scope. Okay. Why? Because there are so many findings from that particular graph. That is the reason. Okay. Next one is a nuclear force. So nuclear force. So already we know. See, now scientists started understanding. Like suppose electron, between electron and electron there is repulsion, right? Between proton and proton there is repulsion. Between neutron and neutron we don't know, and proton and neutron we don't know. So, but still they are inside the nucleus, right? They are friendly inside the nucleus. They are not fighting and coming out of the nucleus. So, scientists started studying about the forces. What is the force which exists inside the nucleus? Then they came to conclusion that it is attractive force. Okay, it is a attractive force, not this one. It is a attractive force. Understood? It is attractive force. The first one is what? The first one. So it is attractive. Nuclear force is attractive. The second one is short range. Okay. The second one is short range. Nuclear force is short range. Short range. How much it is? 10 to the power of maybe 10 to the power of minus 15 to minus 16 meters. Okay. It's a Fermi. It comes in Fermi. It comes in Fermi. Very, very small.
Now protons and protons attractive.
Now inside the neutron, inside the nucleus, they are attractive. Okay. The force is same. So, and it does not depend upon the charge. It does not depend upon the electric charge. It is same. Okay. It is same. Okay. So that is the meaning of nuclear force. So that means what? Between proton, neutron, proton, neutron, the value is same. Okay. It is approximately same. Is it clear? So these are the three properties. Again, there is a small graph here. We'll draw the graph. FMS, femtometer. Femtometer is 10 to the power of minus 15. Okay. Potential energy is MeV. Potential energy is MeV. Indian electron volts. This is minus 100, 0, and then this is plus 100. So it also here this particular value 0. Understood? So nuclear force, it is attractive, short range, and it does not depend on the electric charge. It is same. It is approximately same. So between proton, neutron, and proton, neutron, the force, what I say, your nuclear force remains same. Remains same means the nuclear force. Nuclear force remains same. Okay, that's the meaning of this. Then what is the meaning of this graph now? First copy is attractive short range, then it depends on the short range attractive force. This one. Now, variation of distance. Very good. Yes, sir. Now tell me, what is this? R is given to you and potential energy is given to you. What is the meaning of this here?
So the potential energy depends on the
First of all, tell me what is R here?
radius.
Radius of what?
Nucleus.
Nucleus. Very good. Radius of the nucleus.
So it depends on the potential energy. No.
If it approximately 0.8,
Yeah.
see, approximately at 0.8, it is the minimum.
Minimum.
And the potential energy is how much? Minus 100. What is the meaning of that?
So
Is it minus means what? 100. Minus means attractive.
attractive, yeah.
And positive means
Repulsive.
repulsive. Okay, minus. The negative means attractive and positive means repulsive force.
So
As the radius
the most
increases,
Uh-huh.
it first decreases, then becomes
At
constant.
0.8, approximately 0.8
Yeah.
per meter. Okay, FM. So if we can think about 0.8 FM. What is happening? It is minimum, and it is maximum attraction is possible. Meaning is maximum attraction is possible at that point, and potential energy is what? Negative. Means attractive force is there. More attractive force is there. Okay.
Then the attractive force slowly
As you
becomes
increase the
constant.
radius, then what is happening?
Attractive force becomes zero.
Zero. Okay. Now this also graph tells about about the nucleus. Like example, suppose there are two atoms, like is a something like this, like a diatomic atom, diatomic molecule. Okay. Now this is the normal radius. If you compress this, what will happen? Repulsion will take place. If you stretch it outward, if you stretch it outward, what will happen? If you stretch it outward like this, then the bond will get stretched, and after that what happens? If you keep on stretching,
Will break.
it will break. Yeah, this is the exact example which is in chemistry actually. What is happening? This is a normal thing. When you compress it, this is that is a normal situation between the two atoms. Now when you compress it, what is happening? Repulsion takes place. When you expand it or stretch it outward, then what happens? Attraction takes place. Here there is repulsion, here there is repulsion. Okay, and here there is attraction. Then if you keep on stretching, what will happen? The bond will break. Understood now? The same thing happened here. See here. This is the at this point. What happened? This is a normal thing. This is this point at zero. This zero means what? No attraction, no repulsion. No attraction, no repulsion. As you stretch it, as you compress, that means if you are reducing the distance, what is happening? Repulsion is there. As you stretch it outward at a particular point, the attraction is possible. Yeah. If you keep on stretching more and more slowly, what will happen? The attraction. What is happening to the attraction? Slowly it is decreasing.
Yeah.
It is again decreasing and become at maybe at certain distance it breaks. The bond will break and they are separated. Understood? So that is what we discussed from that particular graph. Okay. Is that clear? So this is the variation again. Now next we'll discuss about the radioactivity. Is it clear? Yes, Joshua. Proton, neutron, proton, neutron, all are attractive, my dear. Okay. There is no repulsion. If you start with repulsion, then it will be a problem. So that is why we are going with only attraction. Okay. Clear? Now next one, we have radioactivity. See, AH better. Okay, he was working in, in 1806. He was working on fluorescence phenomena. You know what is photoelectric effect?
Yeah.
You know what is photoelectric effect? When light incidents on a
Or the
metallic surface, then
surface,
electron is ejected out. Okay, that is it instantaneous process or delayed? Instantaneous process. It is an instantaneous process. That means the time delay is 10 to the power of -9 seconds. But in fluorescence phenomena, he was working on fluorescence phenomena. It is nothing but delayed photoelectric effect. Fluorescence phenomena. It is delayed photoelectric effect. Electron will come out, but after certain time. Okay. Delayed photoelectric effect. He was working on this. So what happens? Light will incident on this salt or something, and electron ejected, and there is a photographic plate here. There is a photographic plate by which we are able to detect that presence of electron. Okay, this is H nu. Now what happened? He was exposing the salts to the like the experiment was like to expose the salt to the sunlight and keep the photographic plate. Then the photographic plate will tell you how many electrons. Whatever that calculation was done. That was the experiment. So actually it was raining for 3 continuous days. It was raining, and he had a photographic plate. The packet he kept it under the drawer of a table, and he was working with some other thing. But later on, when the rain was off, and then he wanted to use the photographic, do the same experiments again. It was a new packet actually, and all the photographic plates were exposed in the same manner. All the photographic plates were exposed. The packet completely was exposed. Then he thought when he in the same manner. Then he started understanding. I did not even open it, and I know it was not even exposed. How come it gets exposed? Then there was some more salts in the drawer. Then he started studying about those salts. Then he came to conclusion that there is a salt called radium, which was giving radiations. Which was giving radiations of its own. It was giving radiations of its own. Okay, radiations of its own. So this was later on named as natural radioactivity. Natural radioactivity. Okay. So then after that, Madame Curie. Okay. So Madame Curie, have you visited the Women Pavilion?
Yeah.
Okay, very good. Madame Curie, Madame Curie started working. Madame Curie and her husband Pierre Curie. Okay, so both of them started working in doing the research on this particular, radioactivity concept. And they started like that. Actually, in those times, there was very less encouragement was there for research. Like it was a private research. You have a lab. This is the thing happens in China also. That is why this corona thing has come out. Okay. So it's like a biowar now. So what has happened? These labs are there. They used to suppose you want to make one lab and take the benefit out of it. You sell the patent and you make the money. It was like that. There was no encouragement from the government. Government sponsored was not there. So at that time they started in a car shed. They started their lab in the car shed, both of them, and they found out an element called polonium. They got a polonium, and for which they got the Nobel Prize. Okay, this was named after Poland. They belong to Poland. So the element name, they named the element. They discovered a new radioactive element, polonium.
So where do you find these elements?
Yeah, in the earth crust. On the earth crust, we find out.
I thought you just go to the beach, pick something.
No, it's not.
Yeah, so I also find like 15 elements.
1 second. Hello?
No, they promise.
All is fine. I mean, can I call you after 5 minutes? What happened? Yeah, I will call you after 5 minutes. I'm in class. Okay. Okay. So this Madame Curie and Pierre Curie, they got Nobel Prize for Nobel Prize for finding this element. Okay, for discovering this element. After that, Pierre Curie died in a tragic accident. Okay, and she continued. Madame Curie continued the research with her daughter Juliette Curie. Okay, so Juliet Curie. Okay, and also they also again find out the radioactivity, the uses of radioactivity and all, and again they got a Nobel Prize together. Okay, so Madame Curie is the only lady on the world who got 2 Nobel Prizes in 2 different subjects, one in physics and the other in chemistry. She got 2 Nobel Prizes. Madame Curie got 2 Nobel Prizes, one in physics and one in chemistry. And the only lady on the world, woman on the world who got 2 Nobel Prizes in 2 different subjects.
So who has the most Nobel Prizes?
I think one more scientist is there, like he is having in the same subject, not in 2 different subjects. I think. Okay, so that is the thing. Actually, they both were prone to, like, exposed to the radiations, and later on they got cancer and they died. So they are, this is the, like, sometimes if you see the lifestyle or the story of the scientists, they sacrifice everything, but they are all unsung heroes. Okay, every scientist is not like it's not about only this man, this Madame Curie and Marie Curie. Even being a lady, instead of so many restrictions, also she worked a lot, and she found out radioactivity. Because of the radioactivity, we are able to save so many lives. See, because of radioactivity, we are able to find out a X-ray. X-ray is a simple thing. Yeah, the X-ray. In X-ray, the source is what? Radioactivity. Again, a radioactive sample. We are not using the high, like in X-ray also, we can use that electrode, a fast-moving electron. Actually, what is happening? The electrode is there, then the element is there, that filament will be there, and when you heat the filament, electron will come out. That electron will go and hit the tungsten, and then electron is released. That we are not doing. We are using the electron, which is or the alpha particle or something which is coming out from the nucleus of a radioactive element. Understood? This was a very great achievement. In MRI, we are using now. Actually, MRI full name is NMRI, Nuclear Magnetic Resonance. When we wrote that NMRI, people got scared, and no one was ready to take a MRI scan. They, for business purpose, they removed N. Now it became popular. MRI means okay, it's okay, fancy now. Understood now? Actually, it is nuclear magnetic resonance imaging. What exactly happens? Like in the actual scan, they give radio cobalt injection. The radio cobalt injection has a half-life period of 52 minutes. Then after that, they take the scan. Then the alpha beta particles start coming out, and they got dispersed. They get deviated due to the very high magnetic field. The person is made to move into the chamber, and then very high magnetic field is given to that. Then the radiations which are coming from the body, they get deviated and they are collected, and that is how we find out exactly what is the problem in the body. Okay, like that we have PET scan also, positron emission tomography, CT scan, computer tomography. Like that, they have different scans now. CT scan, PET scan, MRI scan. There are many scans now. All these are using some or the other way. We are using the radioactivity. Not only that, we are also using radioactivity for what? For medical purpose, for chemotherapy, for saving the patient from the cancer. Like there's a tumor in the body. Actually, what is a cancer? Cancer is a small, unwanted growth in the body. Actually, it's a small bad cell which created everything, which the big headache for the whole body. Okay, generally how it happens. Okay, the food habits. I will tell you one example where the food habits to be improved. What we are doing, simple example. 2 things are very, very important. Generally, it starts from the food only. The cancer thing. Number 1, when we wash the utensils, okay, that we wash with some chemical, right? What is that? Fairy or something. We wash it. Okay, wash it such that, and once you wash it and keep it in the clean water for some time. Let the atoms or molecules of the fairy, let it completely vanish from the plate. What is happening? Even 1 or 2 molecules, they get once you put the warm food, it gets activated again. Once it goes into the body, something else happens. Okay, that is one thing. The second one is in microwave oven. What we do is we use plastic. Plastic safe, we say. It's no more safe. Never use the plastic thing. You know what is happening in microwave oven? The microwave oven. So when you keep the food in the microwave, what is happening? Suppose this is the
cells in the
grains. Suppose this is the food. Okay, I kept some food here. So what is happening? These are the radiations. Okay, the radiations are given to this one. Okay, so what is the frequency? Maybe it is around 2 MHz, 2 million 2 megahertz, suppose that much is the frequency. So what is happening, when you give that, the molecules in the food will oscillate that many times in 1 second. Means that is why we have to pour some water, make it moisture. Liquid food is okay, but other than like solid food, if you're keeping, just make it little moisture, so that those molecules will oscillate, and it will, then what is happening, that oscillating energies or vibrating energies being converted to heat energy. That is actually thing happening here in the microwave oven. So better keep some moisture on it, so that, or wet it, so that those molecules will vibrate and it will convert that into heat energy. And the plastic, they say plastic safe. These plastic molecules, when they are vibrating at that frequency, the plastic molecules definitely it will oscillate, right? It also melts, right? And it contaminates the food. The first microwave oven patent was found in where? In Kanpur, IIT Kanpur, and they sold it to US. That the first patent was found in India only. They sold to US. After that, later on it came throughout the world. Now we have companies microwave oven everywhere now because of that. So this is the one. This is how you have to make it safe. This is how the cancer takes place. Okay. So the cancer. So that is why for the treatment of cancer also we are using radioactivity. So it is playing an important role in the life. After that,
cancer is basically one
bad cell
just kills all the other cells.
Yeah, bad cell. And again there are different types of cancer again. You have skin cancer, blood. First was blood cancer was very famous. After that, many cancer came out now. Skin cancer is there, many cancers. Okay, so so this is a very bad disease. Again, may God bless. From good health. Okay, no one get cancer. Okay, so that is very important. People have to again remove all the hair. People become very weak, and many people died because of the cancer. Okay. So it is about, the first thing is about the food habits. We have to work on the food habits. Okay, better to prepare a fresh food and eat. That's the best way of going ahead with the food. Otherwise, if you are storing it also, when you store it and when you heat it, and you have to take care of this thing. Okay, people don't know about this. Never doing the plastic or better to use some porcelain thing, so it won't contaminate the food. Okay. Okay, so what about dry food? Dry food you have to put some moisture, man. Moisture means like you can apply some butter. Suppose if it is bread, you can apply some butter. If it is like otherwise, you can apply like sprinkle some water droplets on that one. So that is enough. Okay. So I will stop here for today. Okay. The play time is there. Huh? Yeah, we'll see it tomorrow then. Is it clear, Joshua?